Lotte Hollands from Edinburgh, from Harriet Watts specifically. And she's going to talk about, let me start my recording. And Lotte is going to talk about partition functions, BPS states, and abelianization.
Thank you very much, Ron, and all the other organizers for this invitation. Yeah, so it's really nice to be here. So this talk is based on a paper that appeared about 2 months ago with my colleague Richard Sabo and our student Philip Ritter. It is also based on previous works, especially with Andy Neitske, and a lot of discussions with Andy, as well as a paper with my former student Omar Kipai. So this paper is a written up version of lectures that I gave a while ago at a string math conference, as well as this preschool. And unfortunately, due to an illness on my side, it has taken a rather long time to finally publish these notes. In the meantime, there have been a lot of interesting developments in this area, and so what I want to do here is, as well as giving you sort of an overview on this paper, I would like to point out parallels with some recent work, particularly in the context of topological string theory. So the main player in this talk will be the so-called instant-on partition function. And just for those of you who were not so familiar with this object, let me give a brief introduction. So this is a partition function which is introduced for 4-dimensional n equals 2 gauge theory. So basically, it's a summation over q to the power k, as is written here, times the volume of the moduli space, so the moduli space of solutions to the self-dual instant-on equations with instant-on number k. So that is for a pure gauge theory. If the gauge theory contains some matter, which is on the right side, then instead of looking at the volume, we would consider an Euler class of an associated bundle of solutions to the monopole equations. Right. So the main trick in being able to make sense of these integrals is to consider this n equals 2 gauge theory in the so-called omega background. That is to look at it equivariantly and to turn on equivariant parameters epsilon1 and epsilon2, as I call them here, corresponding to rotations in the two planes that make up R4. So if you do that, then you can compute the partition function of this gauge theory, and this is called the Nekrasov partition function. It's a 4-dimensional version of it, which consists of 3 parts: a classical part, which is an exponential of a vector which is proportional to the equivariant volume of R4 times the complexified gauge coupling, and then times what could be what more generally is a sum over the Coulomb parameters of the gauge theory. There is a one loop part, which is a product of double gamma functions, and then there is the instant-on partition function itself, which can be written as a sum over Young diagrams, which label the instant-on configurations at the origin of R4. Right. So one of the important features of this Nekrasov partition function is if you take its log and you consider it in the limit where epsilon1 and epsilon2 are small, then there is a singular contribution, which again goes with a vector proportional to the equivariant volume of R4, but then times a function that I've called f0 here, which is known to be the holomorphic prepotential. So this is an object which characterizes a four-dimensional n equals 2 theory in the infrared. And it was found by Cybercritic a long time ago that this prepotential can be expressed in terms of periods. So there's an associated Cybercritic curve to this theory, and the periods are integrals over this lambda is the so-called Cybercritic form or Cybercritic differential. And these periods, A and A dual, they are not independent, but rather A dual is the graph of the derivative of this prepotential. So notice that all of this is purely algebraic. And what we will see in this talk is that there is also an analytic side to this story. Right, so what I will do is, in this talk, I will focus on four-dimensional n equals 2 theories of a special type, namely they are of a class S. That means that the Cybercritic curve is the spectral curve of a Hitchin integral system, which is based on a curve C. So that is sigma, the Cybercritic curve is a ramified covering over C. So there are two examples that I want to discuss. So the first example is maybe the simplest example of a four-dimensional theory. It's sometimes called the 82 theory. It doesn't contain any gauge-theoretic degrees of freedom, but it merely is a theory of a free massive hypermultiplet field. And in this case, so if we choose our coordinates z and w so that lambda is just equal to w dz, then the Riemann surface sigma may be parameterized by this equation, w squared is equal to z squared plus m, where m is the mass of this hypermultiplet. And it gives a covering, a double ramified covering over just a complex plane with an irregular singularity at infinity. The second example that will play an important role is the original Cybercritic theory, so the pure SU2 theory, whose Cybercritic curve in this choice of coordinates C and W has an equation of the form below. So W squared is equal to lambda squared over Z to the cubed, minus 2u over Z squared plus lambda squared over Z, where lambda is the UV scale of the theory, and u is a parameter on the Coulomb branch. So in this case as well, the Cybercritic curve is a double ramified covering over, well, in this case, it's the complex projective plane with singularities, irregular singularities as Z is equal to 0 and Z is equal to infinity. Right, so most of this talk is concerned with the so-called Nekrasov-Shatashvili limit. That is, we take one of these equivariant parameters to 0. So that means that we're considering this four-dimensional n equals 2 theory on R2 epsilon times just the plane R2, which means that effectively this theory can be described as a two-dimensional theory. And such a two-dimensional theory is characterized by a superpotential. And Nekrasov and Shatashvili, they have argued that this superpotential is essentially a limit of the log of the Nekrasov partition function in 4 dimensions. That is, it starts out with this term 1 over epsilon, which is now the equivariant volume of this R2 epsilon factor times the prepotential. So sometimes in some part of the literature, this superpotential is also denoted as the Nekrasov-Shatashvili free energy. And so what I will use for this is a new symbol, so which is here. So I will write the superpotential as WNS, so the Nekrasov-Shatashvili superpotential in 4 dimensions. So in this particular case of the 82 theory, which was just a free massive hypermultiplet, the superpotential is very simple. It basically has only a one loop contribution. And it's can be expressed in terms of this function y, which is a limit of the 4-dimensional one loop factor. The pure SU2 theory, on the other hand, has a much more complicated expression. So that really has a classical expression, which is given by this term, proportional to the Coulomb parameter squared. Then there is the one loop contribution to the gauge field. And then there is a series in lambda to the 4, which has complicated factors as in this formula. So that's how it starts off with. Right. So the other claim that Nekrasov and Shatashvili made is that this 2-dimensional effective theory in 2 dimensions, that it has a geometric description, and this geometric description is in terms of a quantization of the Hitchin integrable system that we already saw in 4 dimensions, and the quantization parameter is proportional to epsilon. For instance, if we consider the pure SU2 theory, then the quantum Hamiltonians of the corresponding Hitchin integrable system are known to be SL2 opers, and they can be parameterized in this case by a differential operator, which is of this form here, epsilon squared dz squared minus basically the term that we already saw in the description of the Cybercritic curve, which in the limit where epsilon goes to 0 reduces to the Cybercritic curve that we had. I should note that so this parameterization in this middle term 2u plus epsilon squared over 4, this is not necessary. We could in principle choose this term in any way we like. Just happens that this, well, we chose it in the paper because it happens to be convenient for computing various things. Right. So given such a quantum Hamiltonian, you can consider associated spectral problems. That is, you consider this Hamiltonian as a Schrödinger equation, and you look for solutions of it where you restrict your solutions to a special class of functions. This is something that I've sort of talked about in the String Mass conference of this year, and I don't want to focus on these spectral problems here, but I just want to say that what we could do is we could consider these solutions in a WKB way. So that is, we say that psi of z is equal to the exponential of 1 over epsilon times some integral of our function as z. And then once we've defined psi of z like this, we can consider quantum periods, that is epsilon deformations of the usual periods, where instead of integrating over lambda, the Cybercritic form, we integrate over this function s of z. And as was first computed, I think, by Mironov and Morozov, by just quantizing the relation that we had for the prepotential by making an epsilon deformation of this. Instead of the prepotential, we now get the superpotential of this 2-dimensional theory. So what I want to ask in this talk is, can we obtain exact results as well? So it's nice to get this superpotential as in an epsilon expansion, but can we get the exact result from such a reasoning as well? Well, our first example will be again this 82 theory, because it's really such a nice simple theory. So remember that the Cybercritic geometry was characterized by these two surfaces, and that the corresponding Hamiltonians or Schrödinger equations were those of a complex harmonic oscillator. So for this, well, if we consider this Schrödinger equation, then of course there's a two-dimensional set of solutions. But we could choose our solutions to be, so these solutions are parabolic cylinder functions. So what we could do is we could choose our solution, we could choose, consider at least the solution psi1, which is equal to a parabolic cylinder function. Let's see, psi3, which is basically the same, where the argument has an extra minus sign and there is an extra phase. And psi2 and psi4, where we've introduced an extra factor of I in the argument, and some other prefactors, some other phases. So suppose we do that. So these are all solutions of this equation. Then it turns out that we can write the superpotential for this theory as in terms of the Wronskians of these solutions. That is this equation here. So where the superpotential is just equal to half times the integral over dx of the logarithm of the square root of this ratio of Wronskians of the above solutions. So that.
Lotte, could I ask a question? So of course there's a two-dimensional vector space of solutions. Are these all solutions in the Stokes sectors? Is that what distinguishes these?
Yeah, so that will come now. Yeah, is that? So I'll explain how that relates to Stokes sectors right now. Right. So well, this is just to say that we can reformulate the superpotential in terms of these Wronskians of these particular solutions. So, but why is that? Why is that the case? So this is related, as Greg is saying, it's related to Borel with summing. So I want to explain how this is related to Borel with summing. So look at this Schrödinger equation. So the Schrödinger equation has two formal solutions, so two power series solutions, which I've written here as psi minus and psi plus, where psi minus decreases fastest when t is real, and psi plus decreases fastest when t is purely imaginary, where t is related to the z parameter of the on our curve C in this particular way. Right. So so what does Borel sum mean? So if we have a series, say we have this series ak t to the power k, then we can define a Borel transform, and using that Borel transform, we can get the Borel sum, which is an integral of a ray of e to the power minus s times this Borel transform. So this is the Borel with sum in the direction theta. So what this Borel sum does is, if the series that we started out with was convergent, then the Borel sum will just give the same series, the same function back. But more generally, it can produce exact results for, it can resum sort of more general series. So let's apply this technique to this particular differential equation. So the Schrödinger equation with the complex, corresponding to a complex harmonic oscillator. And suppose that this phase is equal to, so suppose that we choose this phase equal to the argument of epsilon, and that we choose it to be equal to pi over 2, and as well as choosing the mass to be real and positive. In that case, psi minus decreases fastest along this diagonal in the C-plane, and psi plus decreases fastest along this other diagonal. If we so if we compute the Borel sums of psi minus and psi plus in each of these four rays, then we recover these functions psi 1, psi 2, psi 3, and psi 4 that I defined before. So moreover, we can analytically continue these solutions. So for instance, in a half plane, so for instance, the solution psi1, the Borel sum psi1 can be analytically continued in this half plane along the green diagonal, above the green diagonal, I should say. So what we get if we do that, if we analytically continue all of these solutions, psi1, psi2, psi3, and psi4, we find the basis of solutions in each of these sectors. So why do we need to take this? Why do we need to consider theta is equal to pi over 2? Well, note that this phase is a very special phase because, well, we were considering the 82 theory corresponding to a massive hypermultiplet, and pi over 2 is exactly the argument of the central charge of this hypermultiplet. So one way to visualize that is through a spectral network. So if we compute what the spectral network would be corresponding to this theory, corresponding to this phase, that is, we look at trajectories which are given by this property. So e to the power minus I theta times the square root of sec squared plus m is real, then we get these trajectories which are drawn in black here in this. So this is a picture again of the Zeeps plane along with the critical trajectory. So there's a trajectory, there are 3 trajectories coming from each of the branch points. And what you see is that there is a special trajectory in between these 2 branch points. This is a double trajectory, a critical trajectory. And this critical trajectory in the theory of using the theory of Gayotto-Moore-Netsky corresponds to this massive hypermultiplet. So moreover, the spectral network, it divides the Z-plane into 4 sectors. And as we saw before, in each of these sectors, 4 sectors, we have a basis of solutions which are given by the Borel sum of these formal solutions to our Schrödinger equation. So these bases, they are very special. They're special in the sense that if you go from one sector to the other, then the change of basis matrix is given by a unipotent matrix. And exactly this fact means that we can well, you can say it in different ways. We can lift this oper to an abelian flat connection on the spectral curve. But it also means that we can compute the quantum periods, the exact quantum periods now, in terms of Wronskians of these solutions, of this basis of solutions. So, so what we get is that that one of the exact periods. So, well, let's see. So, so what I've denoted by XA here, that's the A, the exponential of the A period. It can be written as a ratio of 4 of these Wronskians, as well as the XB coordinate, as well as the B period. There is one subtlety here, which is because this is a critical network, really exact WKB or abelianization is not defined exactly at this phase. So what we do here is we take an average, and that's why we find the square root in the definition of the B period. Now, if we define this, if we impose that this A period is related to the exact Coulomb parameter A in this particular way, so XA is equal to the exponential, basically, of this Coulomb parameter, and XB is equal to the exponential of the dual Coulomb parameter, then by the same relation that we used before, so again, we write a dual as a derivative of the superpotential, then we find the exact form of this superpotential. So the second example that I want to look at is the example of the pure SU2 theory, which has a more complicated superpotential. So in this case, so remember that the Cybercritic curve was given again by a double covering over the twice punctured sphere with irregular singularities at c is equal to 0 and infinity. In this case, the corresponding quantum Hamiltonians are given by the Mathieu differential equation, which we've seen before as well. So it's written down again here. In this case, so how do we reformulate the superpotential in terms of Wronskians? So in this case, we again introduce some solutions to this Mathieu differential equation. Namely, we introduce solutions. Well, we basically divide this twice punctured sphere into 3 regions, and in each of them, we define a basis of solutions. So the solution psi1 would be asymptotically small in this region. That is, if z goes to 0 along the negative real z axis. As well, psi1 prime is, we define it in a similar way. So it's asymptotically small when z goes to infinity along the negative real axis. And these solutions psi1 double prime and psi2 double prime, we define them as the eigenvectors of the monodromy around c is equal to 0. So to define all of these solutions, we need to pick a phase. And in this example, we again pick our phase theta is equal to pi over 2 for reasons that will become clear later. Also, so what I'm doing here is I'm considering the SU2 theory in the weakly coupled region. So I choose, in particular, minus u much larger than the scale lambda squared. Then the reformulation of the superpotential in terms of these solutions is as follows. So the superpotential is equal to half times the integral of dx of the logarithm of the square root of ratio of solutions. And it's not a very simple computation, but you can verify that this indeed gives the superpotential as it is known, at least in a series expansion in lambda to the 4th. So let me sort of briefly sketch how you can verify this. So we verified it by introducing a new coordinate, phi is equal to 0 over lambda squared, near this puncture at c equals to 0, and then compute these solutions in phi in a series expansion in lambda squared. Then you analytically continue them to large phi, to this intermediate region, and reorganize this series as a series in lambda squared. And then you compute these intermediate solutions, psi1 double prime, psi2 double prime, independently as eigenfunctions of the monodromies, also in a series expansion in lambda squared. And if you then compare them, you can you find the Wronskians that we were after. So this computation, order by order in lambda to the 4th, it reproduces the superpotential that that is well known. So what is the physics interpretation of this computation?
Short question.
Yes.
So there was another interpretation of the exact result of some of those that you mentioned of my work, my old work, by Kozlovsky and Teschner for exactly this case. And what they wrote how to write superpotential W in terms of basically in terms of the Baxter operator and so on, which is a Fourier transform of what you have. So
I'm unfortunately not aware of that particular paper.
They proved, you see, our work was such that we would expand not in epsilon. We considered epsilon basically equal 1 or whatever, anything, because it's a parameter. Expansion is in lambda. Instanton counting parameter is lambda. So lambda count instanton sectors. And since the statement was that the instanton expansion gives the quantum superpotential, our argument was that let expand in lambda, but exact in epsilon. So in epsilon, everything is exact, but we're expanding in lambda. In each order, it's easy to prove that in its order, this expansion is doable. And claim was that that expansion of the solution would reproduce a superpotential. And what exactly Kozlowski and Teschner did, they claimed that this expansion was reproduced by integral formulas they wrote. They basically did Riemann solution of Riemann-Hilbert problem and reconstructed the superpotential in terms of Baxter operator, which is again Fourier transform of the size that you have. So it would be good to compare with their relation, because they
this is not the paper by Teschner and Vartanov, is it?
No.
No, it's okay.
Like it was like year after.
I see.
So probably 2010, 2011. They basically showed that in case of periodic Toda, which is this SU2 pure Leiberg-Wittgenstein, that in case of periodic Toda, the problem was solved in the integrable literature by Kharchov and Lebedev. So there was a solution by Kharchov and Lebedev, which was basically what Sklyanin wanted to do. So there was this solution by Kharchov and Lebedev, and Kozlowski and Teschner decided to show that that solution and what we proposed were exactly the same. So they derived the formula. On the left-hand side, you have W is our superpotential, and on the right-hand side, you have solution to Baxter equation, again, which is a Fourier transform of size. So it would be good.
I think, I'll look at that paper
probably it's 2011. I would think like 2011. Just a suggestion.
Yeah, thank you. So I wanted to make a relation to another paper which appeared well, a bit later, I guess, which is a paper by Nekrasov and Jung, who give a gauge theoretic proof of the computation I just showed. So this is in terms of surface defects. So the solutions that we consider psi1, psi2, and all the solutions with primes, they correspond to VEFs of half BPS surface defects, which are located in this R2 epsilon. So the moduli space of these surface defects is the surface C, and by realizing that these psi's have a certain description in terms of a certain description as a two-dimensional surface defect, where, for instance, these solutions psi1 double prime and psi2 double prime correspond to VEFs of a surface defect, which is defined by an orbifold. Nekrasov and Jung were able to get to the same conclusion. Right. So why is this phase theta is equal to pi over 2 in the story? Why is it so important? Again, there is in this case a particle in the theory, namely the W bosons, which exactly have this as their argument of their central charge. So in particular, if you consider the spectral network or Stokes graph at this phase, it will look like the picture on this slide. So again, the black lines are the trajectories of the spectral network, and these trajectories divide the twice-punctured sphere into 3 regions, and in each of these 3 regions, we have a basis of solutions. So in this case, these bases, they are related by a product of two unipotent matrices, because both this and this trajectory are double trajectories. But still, still they can be interpreted as Borel-Richon solutions to the relevant differential equation at this phase. And using the fact that they're special in terms that they define a local basis for the abelianization with respect to the spectral network, we can compute their quantum periods. So that is written down on the slide here. So we find that the A period is just proportional to the eigenvalue of M, corresponding to one of the solutions, to the solution psi2 double prime, and the B quantum, so the quantum B period, it can be expressed by square root of a ratio of Wronskians of these other solutions. Again, we find the square root because this is a critical phase where, such that exactly at this phase we cannot do the abelianization or exact WKB, but we have to take this average. Now, using the same relations as before, expressing the A and the B periods in terms of these exact Coulomb parameters A and A dual, we again find the superpotential by this relation, and that is exactly that exactly gives the formula that we started out this example with. Right, so this can be rephrased based on work of Nekrasov-Shatashvili in the following way. So the statement is that four-dimensional n equals 2 theories, for four-dimensional n equals 2 theories, the superpotential can be computed analytically as a generating function of opers in terms of generalized Fenchel-Nielsen coordinates, because these Fenchel-Nielsen coordinates are exactly the quantum periods that are obtained from the spectral networks at special phases. You can generalize this for any theory of class S. So in a paper with Omar Kitwai, we, for instance, wrote down a description of how to obtain the family of opers corresponding to any theory of class S. Sorry.
That would mean, Lotte, excuse me, that would mean that for high rank case, when you get, let's say, not SU2, but whatever,
yeah,
2n and so on. So as you notice, as you just wrote, the logs of those things on the right hand side have this A epsilon and A dual epsilon, right? Mm-hmm. These are coordinates that we would call with Rossley alpha and beta, which are,
yes, that's right, yes.
So that means that you have a formula for high rank for the coordinates, which actually is not known in general, and there is a reason for that. But anyway, so you have formula.
Yes.
For coordinates.
So yes, that's right. So we have So we have formulas. We have a formula for what the superpotential is in terms of solutions to the relevant oper equations for those equations, for those theories. Sorry. The only problem is that the differential equations that come up for such, for instance, non-Lagrangian theories, their solutions are not sort of a special function type. So that means that their monodromies are actually very difficult to compute. So in other words, the exact WKB analysis in that case is very difficult. So to get exact results in terms of epsilon is difficult. But you can find the superpotentials in an epsilon expansion for those theories using this description. Is that?
No, I was just wondering that you have new formula, it seems to me, because what I understood before was the case, let's say if you take sphere with 4 mark points, the simplest case, and consider gauge group of high rank, then these coordinates we understood only in the case when 2 of those 4 points have a trivial monodromy, which is just one dimension.
Yeah, no, so yeah, so I'm saying
the same problem is in AGT, that you have 2 points are special and the rest of the points have arbitrary monodromy.
Yes. So right. So so using the technology of spectral networks and abelianization, you can find a generalization of Fenchel-Nielsen coordinates for those networks as well. So in particular, we considered the E6 theory with Andy, and so there was a paper discussing a generalized a set of generalized Fenchel-Nielsen coordinates in that case.
For arbitrary monodromies.
Yes.
Okay.
Yeah. So for the E6 theory, so that means 3-punctured sphere with general monodromies around the 3 punctures.
Okay, thanks.
Yeah. So so I think that's that's a very interesting problem to get the exact results for those theories. So this involves some hard analysis, I think. But yeah, in this talk, I was going to focus mostly on the Lagrangian theories. Right, because so the remark that I wanted to make is that so we've now defined, we've recovered the superpotential as a Borel sum in a specific critical direction. But of course, you can consider this Borel sum in any correction in any direction. So that is, you could define a generalized object, a generalized Nekrasov-Shatashvili superpotential, again through this similar equation, but now the quantum periods they are defined as quantum periods with respect to this phase. So you can either compute them as Fourier periods with respect to this phase, or spectral coordinates corresponding to the corresponding Fenchel-Nielsen network. Let's see. Yes. Right. So so it's interesting.
Fenchel-Nielsen network, it can't be more general spectral network.
I'm sorry?
It has to be a Fenchel-Nielsen spectral network?
No. So here, no. So here the phase is completely generic.
So it's a general spectral network?
Yes. Okay. Yes. So yeah. I'm not yet giving a physical interpretation, but you could define an object which is dependent on this phase. So as I was going to say, which jumps whenever there is an active ray. So that is, maybe I should explain this. So if you consider spectral network corresponding to, it changes at discrete phases theta. And these discrete phases, they're sometimes called active rays. So you could make a diagram for each theory where you draw an arrow at the place where the spectral network changes. So that is where something happens in the theory. So the object that we just defined, which depends on theta, it's a piecewise constant function. So it will jump whenever there is an active ray. So in this picture, you can see the active rays for the pure SU2 theory as an example. So at phase pi over 2, that corresponds to the phase of the W boson, whereas there are also phases where the monopole and the dion appear. Right, so you could consider, so how does this object, this generalized object, how does it transform if we cross one of these active rays? And well, the generic active ray corresponds to a flip of the spectral network, which means that the spectral network it changes in this way that I've illustrated here. And if you consider the corresponding coordinates or the corresponding Coulomb parameters, then you find that for such a flip, that the A parameter, it stays the same, whereas the dual parameter, it changes by a logarithm of 1 minus the exponential of the A parameter. That is, it means that this that the superpotential, that it changes by a factor which is proportional to the dilogarithm. Right, so so this makes connection to other things. So for instance, so it shows that this superpotential, this generalized object, that it encodes all 40 BPS states, because the 40 BPS states exactly correspond to these active rays. It also means that it is an object which transforms as a section of a certain distinguished line bundle. And so this is a story which I learned from Andy Neitske, but which has been made precise in a slightly different setting that I will comment on later by Teschner and collaborators. What does this mean physically, this generalized object? So what we think is that that in the 4-dimensional gates theory that we started out with, that this theta labels an IR boundary condition, a boundary condition on infinity of R2 epsilon times R2. So yeah, sorry, it's here. So in other words, it corresponds to coupling a 3D n equals 2 theory at infinity of R2 epsilon times R2 to the 4-dimensional n equals 2 theory in this half omega background. So indeed, well, this formula where we saw that the flip corresponds to the dilogarithm, that exactly corresponds to the 3-dimensional tetrahedron theory. Right.
Lotte, usually you couple a 3-dimensional theory to a 4-dimensional theory on a boundary at finite distance. But it looks like you're coupling it to a boundary at infinite distance. Is that right?
Yes. So yeah, there is a relation there. You could consider it in terms of the cigar geometry of Nekrasov and Witten.
Okay.
Where where it's at finite distance. So that shouldn't change any of the formulas. The other sort of generalization that you can make from this formalism is you can start thinking about Lagrangian theories in strongly coupled regions, or even, well, non-Lagrangian theories. But I was not going to focus on the Lagrangian theories here. I was rather going to say a bit about what happens to the pure SU2 theory, for instance, in the strongly coupled region. You probably know that that the U plane is divided in a recoupling and in a strongly coupled region, and that the 4D BPS spectrum is very different in those two regions, and that means that the spectral networks in these regions are also very different, and that the exact quantum periods will be very different. so what can we say? So still, the opers are still given by the same Mathieu differential equation. It's just now that we look at this different, that we examine this differential equation in a different regime. So there are special phases if we want to connect to the usual formula, to the usual effective twisted superpotential for the pure SU2 theory. We would consider a special phase, and in this case, that would be so if we consider, well, if we would compute this, if we want to compute this superpotential near the Dion point, then the special phase is given by the argument of the central charge for the Dion. So the spectral network at this phase looks as follows. And again, you see that there is this double trajectory here, which corresponds to the Dion. So again, in this case, there is a natural choice of solutions that we can consider. And then we can write the A periods, the exact periods in terms of the Wronskians of these solutions. And we can extract a superpotential. So this is a way to obtain an exact answer, at least exact in epsilon, for the superpotential in the strongly coupled region. Right. So
one quick comment in this place. Just the W is always exact in epsilon, right? Because if you go back to the formula you had in one of the first transparencies, the formula that we had with Greg Moore and so on. So W is written as in each power of lambda is written as exact integral.
Yes, yes.
So in epsilon,
right.
it's exact.
That's right.
It's
as far as I know, in the strongly coupled region, the exact result is not known.
There was actually, okay, let's think again. So we have expansion.
Samson, since we're approaching the end of the talk, maybe can you hold your questions to the end?
Sure.
Just a few more minutes. Thank you.
Sure.
Okay. Yes. Yeah, let me continue, and we'll come back to that later. I want to make a quick remark to something else, namely, instead of looking at this NS limit, we could also consider a different choice of parameters. Namely, we could choose epsilon 2 equal to minus epsilon 1. It would be interesting to see sort of what is the geometric description of the superpotential or free energy in that particular limit. Likely that corresponds to introducing a different type of surface defects that in this case wrap the R2 instead of the R2 epsilon. So there is a whole literature related to the Nakajima-Yoshioka equations that relates the Nekrasov-Shatashvili limit of the Nekrasov partition function to this self-dual limit through these equations. Right. So the last thing I want to comment on is a possible lift to 5 dimensions. So as you know, as you probably know, these 4-dimensional n equals 2 theories, they may be lifted to 5-dimensional theories, which if you consider such a theory on R4 times a circle with radius beta, then in the limit where beta goes to 0, it would reduce to the 4-dimensional theory. And by geometric engineering, such a 5-dimensional theory is related to a certain non-compact toric labial, which by mirror symmetry is related to another non-compact labial of the form uv plus h of x, y is equal to 0. And the corresponding mirror curve, which is defined by this, this function h, which is embedded in this case in c star times c star. This mirror curve is, in the terms of the gauge theory, it would correspond to the 5-dimensional Cybercritic curve, which in the beta going to 0 limit corresponds to the 4-dimensional Cybercritic curve. So just to be complete, so in this case, for these 5-dimensional theories, there is a k-theoretic version of the instant-on counting, where the partition function is given by a certain character with a trace over the holomorphic functions on the k instant-on space. Again, we can take the Nekrasov-Shatashvili limit, which in the limit where epsilon goes to 0 has its has a singular contribution which is proportional to the 5-dimensional prepotential. And well, this Nekrasov-Shatashvili limit, well, the theory in this limit has a dual interpretation again as a quantized Hitchin system. So this time it's a quantized multiplicative Hitchin system, which where the spectral curve is this this mirror curve defined by h, which now defines a ramified covering over c star. So all the ingredients for a lift to 5 dimensions are available right now because, well, we know a lot about multiplicative Hitchin systems, in particular that they also have a hypercalar structure where they're described in the complex structure I by multiplicative Higgs bundles, and in other complex structures by difference connections. Also, well, recently there has been a lot of progress on lifting spectral networks from 4 dimensions to 5 dimensions, known as the exponential spectral networks. And of course, there is a physics interpretation of all the surface defects that we considered in terms of the Clap-Yau, namely they correspond to B-branes, which end on the mirror curve. So, for example, one of the simplest examples is maybe the resolved conifold, which is given by the total space of these O-1 plus O-1 over P1, which by mirror symmetry is related to a Clap-Yau, which is defined in terms of this function h, which is given in this case by simply 1 plus x plus y plus q inverse, where q corresponds to a Kähler parameter, times x times y inverse equals to 0. And you could consider that as a well, as a double covering over C star. So in the 4-dimensional limit, these 5-dimensional geometries, they correspond to the 5-dimensional gauge theory reduces to an 82 theory. And the geometries correspond to the geometries that we've seen before in the talk. Cybercritic geometries of the 82 theory. So you can analyze the BPS, the 5D BPS spectrum, and this is done by work by Banerjee, Longhi, and Romo. So you can find that that there are 3 BPS particles in this case, which correspond to 3 so-called KK towers of D0 branes, which have a D2 charge equal to 0 plus or minus 1. So in the 4D limit, where the KK momentum goes to infinity, this corresponds to the hypermultiplet as well as the anti-hypermultiplet that we've discussed in the 82 theory. So the spectral networks, they're quite interesting, and if you consider the phase diagram, so if you consider when they're active rays, when this network flips, it looks a lot like the pure SU2 theory actually. So it's drawn here, and again there is a special phase. So the phase theta, well, again it's the phase where theta is equal to theta is equal to pi over 2, in which this network has a Fenchel-Nielsen type shape. That is, it divides the surface in certain regions. Well, all of the trajectories are double trajectories. So essentially, what it does, it divides the curve, the spectral curve in this case, which was defined by H. It defines it in 5 regions. So a local basis of sections in this case is given by again by fefs of surface operators, or in other words, by B-brane wave functions. And if you apply the same strategy that we've applied before, you would consider periods, A periods and B periods, where the A period in particular is just given by the scalar parameter Q, whereas the B period is given in this case by the ratio of these psi's, where we analytically continue one of the B-brane wave functions. Well, so we consider this path, and we analytically continue one of these wave functions to the other infinity, and then we compare it to the wave function there. So that will be the natural definition of the B period in this case. So this has actually been considered before, this example, in a somewhat older paper by Akanajic, Chen, Dijkgraaf, Kreffel, and Vafa, where they exactly considered these periods and recovered the superpotential, the 5-dimensional superpotential, as in terms of these quantum periods. So this would be in sort of the easiest example that you could think of in 5 dimensions. Now, if you change this phase, if you would consider this more general superpotential, then again, as before, the superpotential picks up these factors, which are proportional to the Lie logarithm, and so this relates very nicely to some recent work on non-perturbative structures in the topological string theory in the self-dual limit. In that work, you would do something similar. So Alim, Saad, Teschner, and Tully, they start out with a formal series expansion of the free energy of the topological string in the self-dual limit, and then they apply, they compute the Borel sums corresponding to these different phases. And as in the case that we just described, they discovered that at this particular phase, theta is equal to pi over 2, you find the usual, well, the well-known topological string free energy, which is the Gopa-Kuma-Vafa one. But very interesting, if you compute this Borel sum at a different phase, namely theta is equal to 0, you recover another object, well-studied object, namely the non-perturbative definition of the free energy as it was defined by these people below. So this makes right. So so this relates this whole project to a couple of other developments. So, for instance, it translates it as a Riemann, related to the Riemann-Hilbert problem, as was studied by Bridgeland, and it relates it to non-commutative Donaldson-Thomas invariants, as were studied a while ago by Centroy and Jafferis and Moore. Right. I think it's time for me to stop. And yeah, that was actually the end of my slides as well. So yeah, thank you very much. And I hope to see you sometime in Edinburgh.
Thank you, Lotte. Don't run away yet. I think there might be a lot of questions. So I think Sheldon was first.
I was applauding.
You were applauding, sorry.
And given the opportunity to say it verbally, thank you very much, Lotte, for a great talk. But I will defer to others for questions.
Thank you.
Yes, so I think maybe, Greg, were you raising hand or were you also applauding?
I was also applauding, but I do have a question.
Go for it.
I actually have two questions. First of all, is that really what it looks like in Edinburgh? That's well, really,
I mean, if you come here, if you would visit, you could take a trip to yeah, where it looks like this.
It's pretty spectacular. The other question is, could you elaborate, please, on the relation to the Nakajima-Yoshioka blow-up formula? I didn't quite see. I mean, what does a blow-up have to do with any of this? And I'm familiar with the blow-up formula and Donaldson. Yeah. So I'm quite intrigued.
Yeah, I didn't give.
You invoked it twice, so I'm very intrigued.
I see. Well, if you look at this formula, it has factors which contain the Nekrasov-Shatashvili limit of the partition function as well as the self-dual limit. And I think that's usually how it's been used. So I didn't give many details.
Does that have to do with the blow up in Donaldson theory, where you have a four manifold and you blow up at a point, you relate the Donaldson invariance from things.
Yeah, so it's similar. So, but I didn't give details about this because I don't have a conceptual understanding of how it relates these two limits.
Okay, so for you, the formula just relates to specializations of the epsilon parameter.
That's right. That's right.
Okay. Actually, Greg, what it does, it's if you have epsilon1 over epsilon2, some rational number like n1 over n2, it relates them. But it is similar to blow-up formulas that you know. It's just what it happens that you have to include epsilons in the business, and then it relates at different points of epsilons.
Mm-hmm. Yeah, but I think it would be nice to have a more conceptual understanding of this, but I don't have it at this point. Are there
other questions? So let's everybody thank Lotte Hollands again for the beautiful talk. And we'll see you all in 2 weeks.
Thank you very much.
And maybe we'll see you in Scotland. Bye-bye.
Bye-bye.